We are still in chapter 5. Chapter 5 has all been about trigonometric identities. And so what have we done? We've done the fundamental identities, which we learned at the beginning of the chapter, like in 5.1. And then we learned sum and difference identities after looking at the fundamental identities like sine, cosine, or tangent of angle A plus angle B or angle A minus angle B. So we learned the sums and differences of identities. And at this point, we are on 5.5, where we want to look at double angle identities and applications of those. And so in particular, a double angle identity means when you have twice a particular angle. So example of what a double angle identity looks like, just going to say like, if we had sine of 2 times some sort of an angle, like 2 times theta. So a double angle identity is basically saying when you're taking the sine of doubled an angle, like twice an angle. So let's see how we start to imagine an identity like this. So they're starting with cosine, and it says we can use the cosine sum identity to derive a double angle identity for cosine, or double angle identities for cosine. So if you want to have cosine of twice an angle, well, we could imagine that you got 2 times the angle by taking the angle and adding it to itself. So 2a is the same as a plus a. And then we could at least plug the a and the a into the sum cosine angle formula that we have instead of a and b. And they plugged it in here. And now because all of the angles are the same, then all of a sudden that allows us to simplify what we normally use in the cosine sum identity all the way down to cosine squared A minus cosine squared B. Because instead of having if this were a B, we'd have a B here and we'd have a B here, and we wouldn't be able to combine those. But since they're all A, it collapses down to just being the difference of cosine squared minus sine squared, all of the A angle. And so we then have cosine of 2a is equal to cosine squared A minus sine squared A. So let's take a look at just a little made up quick example to see how this would help us. And we could even do this with things there where we know the values already. So let's say I had something like the cosine of 60 degrees. Well, we can recognize that 60 degrees is twice as much as 30 degrees. So I could think of this as being the cosine of 2 times 30 degrees. Now, again, in this example, we wouldn't need to do that because we can figure out the cosine of 60 degrees. That's one of our commonly used angles. So cosine of 60 degrees, for example, we know is 1/2. Because that's the x angle, the x value of the 60 degree angle in the unit triangle, and that's a 1/2 value. However, what we're going to do now is recognize that you could get that 1/2 value using this identity if you thought of the a value being 30 degrees, then 2a would be 60. So that means that in this case, cosine of 60 degrees, which we just separately happen to know is 1/2 because it's a nice angle that we've worked with, should also come out to be 1/2 if we instead took the cosine squared value for 30 degrees and minus from that the sine squared value of 30 degrees. Let's put that in parentheses. So let's see how that would work out. So the cosine of 30 degrees So cosine of 30 degrees is square root of 3 over 2. And so that we would get that value and then square it. And the sine of 30-degree value is 1/2. The y value at 30 degrees is 1/2. And we would square that. And so supposedly, if we do that, this is supposed to come out to be 1/2. So what would we get here? The square root of 3 over 2, if you square it, gives you 3 over 4. And then if I take a 1/2 and I square it, I get 1 over 4. And then if I subtract those, 3/4 minus 1/4 is 2/4, which is the same as 1/2. And so this is, at least in this example, helping us see what this identity says and that it is true in this example, but how we could calculate this. And so we wouldn't need this identity to calculate cosine of 60 degrees, but we can see that you get the correct value when applying this identity. And this kind of shows us what the identity says and how it works as well. So let's see what they want to do with this. Oh, no, they're going to go over here to different ways to format that. So when we have this result here, this, because of other identities we have, could be rewritten a couple of different ways. So we're going to get a couple different answers for cosine of 2a. This is one answer, and then we're going to see a couple different ways we could format how cosine of 2a of this double angle could be calculated different ways. So it says here, there are two alternate forms of this identity. So here's the first form. Cosine 2a equals cosine squared a minus sine squared a. But then they're saying, well, what if we took this cosine and converted it into a sine? Because cosine squared a is the same as 1 minus sine squared a. Then we'd have only sines in our answer, and we would get this new format for cosine of 2a. And so what's the value of this? Well, the value in this case is if you wanted to evaluate cosine of 2a in terms of a instead of in 2a, and you only wanted to use sine function, like maybe you just knew the sine of a, well, then this gives you to do it without having to figure out cosine of a. So the original thing here, we have a cosine and we also have a sine, but now we have only a sine function in our formula. So the value of that is that we can evaluate cosine of 2a just using a sine function value, just using sine of a. Similarly, if we take the exact same thing and we say, well, I'd like to just evaluate this in terms of cosine of a, then we can replace the sine squared part with what it's equal to in terms of cosine. Again, this goes back to our fundamental trigonometric identities. And then I would need to simplify like terms here, which would mean distribute the minus sign. Minus of a 1 is -1, and minus cosine becomes plus cosine squared a. And if I take the plus cosine squared a with the other cosine squared a, it ends up combining to be 2 cosine squared a. And so this gives us another alternative form, which has only cosine a in the formula to evaluate. So with the double angle formula for cosine a, let's see if they summarize that actually. No, they switch over to the sine, which we'll do next. So let me get 3 answers. First, there's the original answer. They said, here's identity 1, here's identity 2, and then in the end, we have identity 3. 1, 2, 3. So cosine of 2a can be evaluated or converted into cosine squared a minus sine squared a, or into 1 minus 2 sine squared a, or into 2 cosine squared a minus 1. All 3 of those are the same as cosine 2a. All right, now they're going to do the same thing for sine, because we also have a sum angle for sine. We could use the sine sum identity to derive the double angle identity for sine. And so again, they say, well, let's recognize that 2a could be written as a plus a, and then use the sine sum identity. And it ends up simplifying to just 2 sine a cosine a. So the sine identity here, we have sine of 2a equals 2 sine a cosine a. So again, just to see how this is allowing us to work this, as an example, let's note that sine of 60 degrees would be the same as sine of 2 times 30 degrees. And so the sine of 60 degrees is the y value of the point on the unit circle at 60 degrees, which if we draw that out or look at it, we can see is the square root of 3/2, one of our more commonly used angles and values that we work with. And so apparently we should get that if we instead use this double angle formula and do a sine and a cosine of 30 degrees. So this means that sine 60 degrees, which we know should come out to be the square root of 3/2, just to check, should be equal to 2 times the sine of 30 degrees times the cosine of 30 degrees. Where we're letting a be 30 degrees, so 2a ends up being 60 degrees. Well, so sine of 30 degrees is 1/2, and cosine of 30 degrees is the square root of 3/2. So that means I would have 2 times 1/2 times the square root of 3/2. And 2 times 1/2, when you multiply those, they kind of are reciprocals. You just get a 1, those cancel out, leaving you with the square root of 3/2. And we know that is the value we're supposed to get because that's the sine of 60 degrees. And so this is just highlighting with a simple example what this theorem says and confirming that it works in this simple case. So now we have a formula for sine of 2a, sine of twice any angle. Now that we know a formula for sine and we know multiple formulas for cosine, we could evaluate a double angle formula for for tangent, because tangent is sine over cosine. And so in this case also, we had the double angle formula for tangent we could apply to simplify it there and see what we would get. So still using the fact that 2 times a could be written as a plus a, then we would use the sum angle for tangent and plug in a for both angles. And then you get tan a plus tan a instead of tan b over 1 minus tan a times tan a instead of tan b. And so on the top, we're adding the two are the same because now they have the same angle. So if I combine the tan a's in the top, I get 2 tan a. And on the bottom, tan a times tan a is tan squared a. So we now get a formula for the tangent sum identity as well. So here they are summarized. And the thing to notice is that there's 3 different ways that we might use an identity when dealing with cosine of a double angle. And then there's one for sine and one for tangent. And in each one of these cases, like all of our previous identities, they could give us stuff on the left and ask us to convert it to something on the right in order to evaluate. They could give us things on the right, and then we would replace it with what's on the left of the equal sign. As we've seen with the identities in the first 4 sections of this chapter, they use them in different ways. And sometimes it's to get new identities. So this is our nice little summary here. And then we will refer back to this when we need to as we start to learn these. And let's look at the examples that they give to help us with this. So in this case, they say finding function values of 2 theta given information about theta. So if we knew, like looking at the cases above, if we knew cosine of A or sine of A, well, then we can now say, using these formulas, we can figure out cosine or sine of twice A. So if you know 30 degrees, you can use it to figure out 60. If you know 45, you can use it to figure out 90. If you know 15, you can figure out 30 with it or whatever. We can use one angle information to find the value of twice that angle. So in this case, they're saying, given cosine of theta is 3/5, and sine of theta is greater than 0. I'm sorry, is less than 0. So sine of theta is less than 0 is telling us that the y value of the point is negative, because remember, sine of theta is the y value of the point. And when we know cosine theta is 3/5, cosine is positive, then we basically know something, that we have a point where the x value is positive and the y value is negative. So this tells us the y value of the point is negative. And this tells you the x value of the point is 3/5, but specifically that it's positive. And so these 2 bits of information together help us see that this theta value has to be in quadrant 4. Because in quadrant 4, that's the place where the x value is positive, but the y value is negative. That's kind of why they tell us sine of theta is less than 0. All right, so given this information, they want us to find sine of 2 theta, cosine of 2 theta, and tan of 2 theta to find everything. So since we know the exact value of cosine of theta, we can always use that to find the value of sine theta if we know which quadrant it's in. And so that's how the problem begins. It says it shows them using the fundamental identity that we started with, that's sine squared plus cosine squared equals 1. And then they plug 3/5 in for the cosine, because then the only thing we don't know is the sine. So if you get that plugged in there, and you get sine squared theta plus 3/5 squared equals 1. So they're not showing that here, but I'll point this out. 3/5 squared would be 9/25. And so what they then do is they subtract 9/25 from both sides, so that this cancels out. And that leaves them that sine squared theta is equal to 1 minus 9/25, which is 16/25. So that's how they get this. Then, how do they get to the next part? You would square root both sides, and you'd have to use a plus or minus. But because we're in quadrant 4, and the sine is the y value, which is negative, or that they told us up here, sine is negative, that means that when we have the plus or minus the square root, we take the minus value. And so by doing that, they're able to get that sine theta is minus 4/5. Now, why are we doing this when we want the value for sine 2 theta, cosine 2 theta, these kind of things? Well, the truth is, to find cosine 2 theta, we could have done that just with cosine. We could have used this one here and just plugged in the cosine value to get cosine of 2a. But they also asked us to find sine of 2a and tan of 2a. And for those, we need to know sine and cosine. There's no other choice about it. So that's why they began by, since they told us cosine, they said, all right, to do those other ones, we're going to need to know what sine is. So they begin by finding out what the sine value is. Then once we know that, we can start finding sine, cosine, and tangent of 2 theta. So for sine of 2 theta, the formula is that it's 2 sine theta cosine theta, which we now know both of those. So they plug in the negative 4/5 for the sine and the 3/5, which was given right in the beginning for the cosine, and they do the multiplication and they get their answer. Similarly, for the cosine, now they could have actually done that without the value of the sine by just using the version of the cosine double angle formula that only involves cosine. But now that they have the sine, they go ahead and use the original format for the identity, which is that it's cosine squared theta minus sine squared theta. And for cosine, they plug in the 3/5. And for sine, they plug in the negative 4/5. But when you square it, it comes out positive anyway. And they get this difference, and then they subtract to get the answer, negative 7/25. Well, once you know well, I'll point out, if you know sine of 2 theta and cosine of 2 theta, we don't need the identity to figure out the tan of 2 theta because tan of 2 theta is going to be sine 2 theta divided by cosine 2 theta. So I would just take the sine value and divide by the cosine value to get the tangent to 2 theta, put the theta in there. We don't even need the tangent double angle formula for that, but let's see what they do. Yeah, they did the same thing. They do show interesting. So no, they're not doing the same thing. They're making it much worse. Interesting. That seems kind of silly. But nonetheless, let's see what they did so that we understand it. But let me just show you how what they did was silly after that. Okay, so finding values of 2 theta. Now we're supposed to find tan. Well, the goal was to find tan of 2 theta, tangent of 2 theta. So let me point out here, the goal is to find tangent of 2 theta. So what they say is now find tangent theta and then use the tangent double angle identity. So let's just see how that worked out. That seems silly, but nonetheless, it should still get the right answer in a much longer path. So now that we know sine and cosine, because from the given cosine, we figured out the sine, then we can figure out tangent. Tan theta is sine theta over cosine theta. So they took sine divided by cosine, and they simplified to get this value. So now that's tan theta. Then there's the double angle formula. Tangent of 2 theta is 2 tan theta over 1 minus tan squared theta. And so they plug negative 4/3 in for the tan thetas there. So 2 tan theta is 2 times negative 4/3. 1 minus tan theta squared is 1 minus negative 4/3 squared with PEMDAS in parentheses, correct there. So they do all of that. Yeah, it just seems very strange. Anyway, so they get this numerator. They need to get a common denominator, so they multiply this by 3/3 to get 6/3. Except that's a product. I just made a mistake there. No, we don't need to get a common denominator because we need to get a common denominator on the bottom. On the top, they just multiplied the 2 you'd put over 1, and 2 times 4 is 8, and 1 times 3 is 3, giving you negative 8/3. But on the bottom, they end up with 16/9, because a negative times a negative is positive when you square it, and 4 squared and 3 squared are like that. And then to get a common denominator of 9ths, the 1 I would write is 9/9. And 9/9 minus 16/9 is negative 7/9. So in the bottom, they get negative 7/9. In the top, they get negative 8/3. And a negative divided by negative is positive. And 8/3, if you're dividing by 7/9, then you would change the division to multiplication of the reciprocal. So that would give me 8/3 times 9/7. And 3 goes into 9 3 times. So on the top, I get 8 times 3 is 24. And on the bottom, I have 1 times 7, which is 7. Do they do that the easier way next? There we go. This is the one I was just saying. So up here, I was saying you can use the tan 2 theta is just sine 2 theta divided by cosine 2 theta. And I'm happy to see that they do that here alternatively. All right, I don't feel too bad then. I was saying, come on, guys, you can't expect students to think this is the best way to do the problem. But they don't. They just show you could use the double angle formula, or you can just directly use, now that you know sine and cosine of 2 theta. So alternatively, to find tan of 2 theta, we could find the quotient of sine 2 theta and cosine 2 theta, because we both figured both of those out. So when they make the fraction of sine of 2 theta being negative 24/5 divided by cosine of 2 theta being negative 7/25, they get 24/7, which is the same answer we just got here. Again, this part is still often confusing for students. Well, first of all, negative divided by negative just becomes positive. And then we have 24/25 divided by 7/25, and a fraction divided by a fraction. You change division into multiplication by flipping the right fraction using the reciprocal. And in this case, the 25ths and 25 cancels, and that's how they get 24/7. And that's considerably less work than all of this stuff they did here. All right, so that's example 1. So in example 1, we found cosine of 2 theta as well as sine of 2 theta. We found both of those. And then we also found tan of 2 theta. And all they gave us was cosine theta, and that the sine function came out negative. And then we found all 3. So this is a good example of how you can use these double angle formulas. All right, so let's see how we're going next with these examples. As we've seen with these identities, you can do lots of different things with these identities. This one, it says, find the values of the 6 trigonometric functions of theta if cosine 2 theta is 4/5 and theta is between 90 and 180 degrees. So this one is kind of backwards from what we just looked at, because instead of giving us cosine of a single theta and then asking us for the double theta angle, they're giving us the double theta and then asking us to go back and figure out what theta or the trig functions for all the theta values would be. So they point this out. They say we must obtain a trigonometric function value of theta alone instead of a 2 theta. And again, when you look at these identities, so let's look at the one they've written here for us, these double angle identities. Well, on the left is the double angle, but then on the right is the single angle. So if, like in example 1, they give you the single angle, then you can use it to find the double angle. But if you have, like in this problem, they're giving us the double angle, well, then you can plug that in and then turn around and go back and try to find the single angle that's on the right side. Now, we'd have to do some solving here, but then you can do that. So we replace cosine 2 theta with 4/5. So 4/5 equals 1 minus 2 sine squared theta. And so then what did they do? They solved for sine squared theta by basically subtracting 1 from both sides, so that canceled out. And let's just go ahead and see what would happen. And then they divided both sides by -2 to get sine squared by itself. So if I subtracted these, -1 plus 4/5, that's -5/5 plus +4/5 gives me -1/5. And then they divided by -2, and -1/5 divided by -2 is the same as being multiplied by the reciprocal, negative 1/2. And negative times negative is positive, and 1/2 times 1/5 is 1/10. So that's the steps that they didn't show, that they just assumed you would do by yourself to get the sine squared equals 1/10. And then to solve for sine theta, we would square root both sides, where again, you'd have to use a plus or minus. But then they gave us this information about theta. When theta is between 90 and 180, well, then we know from that range of values that it's in quadrant 2. So theta is in quadrant 2. And that means that sine of theta has to be positive. So when we take the plus or minus square root, we can ignore the minus and just take the positive square root. And that's how they conclude. So doing that, they were able to get sine of theta. Well, they want the values of all 6 trigonometric functions. Well, as we've seen before, if you know sine, then you can figure out cosine, especially if you know which quadrant you're in. And if you know sine and cosine, you know all the rest of the functions. So let's see how they would proceed with this information. So they're actually sort of drawing a picture to use a sort of a Pythagorean approach. We could do it by solving equations, but we could also use it using the SOHCAHTOA sort of acronym to help us. And this is kind of a nice way to see it. So let's take a look at their particular way. Now we could, again, use the fundamental identities. If you know sine squared plus cosine squared equals 1, then if you know the sine value, you can plug that in and solve for the cosine value. But let's take a look at how they're doing it here, because it gets the other values pretty more quickly. So it says use a right triangle in quadrant 2 to find the values of cosine and tangent. So what did we just figure out from above? We figured out that the sine value is the square root of 1/10. So how could we use the right triangle in this quadrant to do that? Well, they're basically saying, we know here's our angle theta. So they're showing us the angle theta and drawing the line. And so we know that for that angle theta, the sine of theta is equal to the opposite divided by the hypotenuse of the reference angle triangle. So we have our reference angle triangle here. And they're saying the opposite over the hypotenuse needs to be equal to 1 divided by the square root of 10. Because if I take the square root of 1/10, square root of 1 is 1, square root of 10 is in the bottom. They rationalize the denominator up at the top. But if I know that opposite over hypotenuse needs to be equal to 1 square root of 10, then I could just make a triangle representing that, where the opposite is 1 and the hypotenuse is square root of 10, which they said here, y equals 1, and the radius, which is the hypotenuse, equals the square root of 10. Then if I know that, I can use the Pythagorean theorem to find the x value in this triangle. So that would, they got a -3 here, but just to show that in action, that would mean that that's a squared plus b squared equals c squared in this triangle. And so a squared we'll say is the x value we don't know. B is a 1, and the c is the hypotenuse is the square root of 10, which would be squared. So this means a squared, the bottom, is equal to 10, square root of 10 squared is 10, minus 1 squared is 1, which is 9. And since a is squared, that means the length of a is equal to the positive or negative square root of 9. And again, since we are in the going to the left here at 180 degrees along that line, we know the length of the bottom is 3. And in this case, it would be a -3 in terms of our x position here, because we are going to the left in quadrant 2. And so they filled in the -3 from the Pythagorean theorem. And why did we go to all this trouble to draw this triangle to find this missing value? Because when we know the opposite and when we know the adjacent and when we know the hypotenuse for the reference angle, then all 6 trigonometric functions follow from that. Now we already know the sine, but cosine will be the adjacent over hypotenuse. So they do that here, adjacent over hypotenuse. And that gives them -3 over root 10. Tangent is opposite over adjacent. So that's 1 opposite over adjacent. So that's -1 over -3 or -1/3. And then they do the same thing for cotangent is adjacent over opposite. Secant is the reciprocal of cosine. Cosecant is the flip of sine. And then they get all 6 functions that way. Now, we could have just, without setting up this big triangle, we could have used the sine value to get the cosine value. And so let me just demonstrate that in case all of that triangle stuff was confusing. So I'm just going to put note here how we could find cosine. So I'm going to put that sine squared plus cosine squared equals 1 in the very short notation. In this case, sine is square root of 1/10, or right above, basically, even simpler, just right above, we already know sine squared is 1/10. So that means 1/10 is sine squared plus cosine squared equals 1. So cosine squared equals 1 minus 1/10, which is 9/10. And then if I square root, cosine is equal to the positive or negative square root of 9/10, which is positive or -3 over the square root of 10. And then because I know theta is in quadrant 2, cosine is the x value, so I know it's negative. So then I know cosine theta is -3 over the square root of 10. So that's the way we've been doing this kind of given sine value, find the cosine value if you know which quadrant you're in. That's how we've done that in the past. So I do like that they showed this triangle here, but notice we could have gotten this -3 over root 10 value for the cosine just by using the trigonometric identity that sine squared plus cosine squared equals 1. And that might have seemed a little easier. And then once you know cosine and you know sine, then you can make the other 4 trigonometric functions by making fractions of these. Tangent is sine over cosine, cotangent is cosine over sine, et cetera, using these values. All right, so there's their triangle approach from this case, or the approach that we've used in the past. But we used we began this by being given information about cosine 2 theta and the quadrant that theta was in, and we used that to figure out cosine and sine of theta, ultimately, and all the other functions as well. All right, let's see example 3. Now, this is one where we're supposed to verify an identity. So this is the other kind of identity problems we've been working with in these first 4 sections as well. And so the identity we're supposed to verify is that cotangent of x times sine of 2x is equal to 1 plus cosine of 2x. And so we had some different approaches to verifying identities. So we are given something that's equal, but we're supposed to verify it. And so the basic idea was you could kind of start with the left and try to work with it until it matches the right. Or you could do vice versa, starting with the right and try to match the left. The suggestion was usually to work with the side that you think is more complicated and then see if it can be simplified down to the other side. So they kind of do that here. So they start with the left. So there's the left of the thing that we want to verify. And in the left, you have a cotangent of x, and you have a sine of 2x. So we know we have a double angle formula for the sine of 2x, which is 2 sine x cosine x. So when we're done and get this just in terms of x, we could get all of this in terms of x. Right now, one part's in terms of 2x and the other part's in terms of x. So if we get it all in terms of x, then the sine of 2x would translate like that. And cotangent is cosine over sine. And then if we did that, we could do some simplification. So that's what they do. They say, all right, the cotan of x becomes cosine over sine. That's what they do in step 1. And then in step 2, they said, and the sine of 2x becomes 2 sine x cosine x. Quotient identity and double angle identity. Well, then we can simplify because this sine x is a multiplied. These are like all over 1. And that cancels with that sine x. And then we have a 2, but we have cosine x times cosine x. So we can write that as just 2 cosine squared x. So that's a simplification. They began by saying, all right, let's take the more complicated side and just simplify it as best we can. And they did. However, we don't end up with what's on the right side, because on the right side, you have cosine 2x. So then we have to take this simplified thing we got and try to see how that could be written as cosine 2x in some way. And so we can look at how cosine 2x is related. Whoops, that's not what I want to do. To cosine x. One of our formats for cosine 2x involved just writing it only in terms of cosine x instead of in sine and cosine or things like that. And so what we can do is, if we do that, we can replace 2 cosine squared x, or I'm sorry, we can see the cosine squared x is sitting inside right here of what we, of this expression. There's the cosine squared x. In fact, times 2 already. We don't even need the times 2. And so the thing that we have here could be replaced with a double angle if we just add 1 to both sides. So what they did here, in case it wasn't obvious, was they added 1 to both sides of this identity, which would tell us that 2 cosine squared x, which is what we were left with, is the same as cosine 2x plus 1, because these cancel out. And that is what we were supposed to get for the right side. So that's how they get it, the left side to match the right side in the end with this swap. So again, this is helping us further practice using these newer identities, the idea of verifying an identity. And you kind of want to look at what you're given, start with one of the sides usually, and then just try to simplify it as best you can. But then you have to keep in mind that you're in the end trying to make it match what the other side was in the beginning. And that may cause you to do some extra work in the end, as we did here, to match up with the identity that we were supposed to verify. Questions about any of that?
What is the meaning of like double angle identity?
Well, the name comes from the idea that in each of the double angle identities, let's go back to the summary here. In each of the double angle identities, you are trying to look at a trig function of twice an angle that was doubled. Does that make sense?
Okay. Okay.
Double angle in this case means the angle was doubled, meaning multiplied by 2. So that's why. Is that okay?
Yeah.
Okay. Other questions at all? What we looked at example 3 here. All right, about 10 minutes left. So let's keep going, see how much of these we can get through. What else do they want us to do? Let's look at their example 4. Simplifying expressions using double identities. So it says simplify each expression. So here's the expression that it started with in example A. We have sine squared 7x minus, I'm sorry, I'm always getting this backwards. Cosine squared 7x minus sine squared 7x. Now, just to think about using identities, if that was a plus, if it was cosine squared plus sine squared of the same angle, the whole thing would just be a 1. But the fact that it's a minus now causes it to match the double angle formula. So I would suggest, as you're learning what the double angle formulas say, kind of compare and contrast them to other formulas. Like notice, if I have cosine squared A plus sine squared A instead of minus, that's just equal to 1. That's our first fundamental trig identity. So if you see a cosine squared and a sine squared of the same thing, well, if they're added, you get a 1. And if they're subtracted, it's not as simple as a 1, but you do have an identity that helps you with that. So in this case, they're saying, well, look at this. We have an identity because this looks just like the cosine double angle identity, that cosine squared 7x minus sine squared 7x, if 7x is the A angle, that would be just cosine twice that angle. Cosine of 2 times 7x, which is cosine of 14x. So we weren't able to evaluate this because we don't know what x is, but cosine of 14x is drastically simpler than the difference of the squares of cosine and sine of 7x. It's just a much, much simpler expression. So I think the real thing when we're using these double angle identities for simplifying is, if I go back up to all of our double angle identities here, just for a second. Sorry if I'm making you nauseous by all the scrolling. Is let's take note of the fact that in all the double angle identities, whatever they gave us on the right side of the identity is a lot more complicated than the double angle on the left. So then in all of these cases, if you're going from the right side to the left side, that will be a simplification. It's simpler. It's simpler if you take the expression on the right and convert it into the left. So if you are given something that looks like any of these identities on the right, and the goal is to simplify, then by matching it up with the identity and using it into the double angle side, then you're going to get a simpler expression. So that's the purpose of this. I think it was the 4th example, right? Getting dizzy. Here we go. So we see, oh, this is the right side of one of the cosine 2a double angle formulas. And so we can simplify by converting it into the left side. So then we can do the same thing here. Let's talk about how you would be motivated to simplify this. They're asking us to simplify sine 15 degrees, cosine 15 degrees. They're asking us to simplify that. Well, that doesn't exactly match what we had, and they're showing what we had down here. So let me highlight what they ended up matching it up with. Well, a product of sine and cosine was the result of the sine double angle formula. The difference is there was a 2 out in front of it. So they're basically, in this problem, they say here to multiply by 1, but how would you know to do that? The way you know to do that is you recognize that, well, what I'm given here looks almost like the sine double angle formula if only there was a 2 out front. So what they do is they put the 2 out front, but you can't just multiply by 2 without changing the value. So then they also multiplied by 1/2. So they're going to say, I want a 2 out front. If I'm going to put that there, I need to also multiply by 1/2, because 1/2 times 2 is just 1. And that means I didn't change the value of my expression by multiplying by 1. So that's what they're referring to here. But the reason they did that is now that when you add the 2 there, or when the 2 is multiplied by the sine and the cosine, now it looks like the right side of the double angle formula. So that part ignoring the 1/2, can be replaced with the double angle formula. So instead of sine 15 cosine 15 all times 2, I can just do sine of 2 times 15. And in this case, I could even evaluate that. We don't know what sine and cosine of 15 degrees are normally. That's not one of our friendly angles, but this product can be simplified to sine of twice that angle, and sine of 30 degrees we know is 1/2. And if I multiply that by the 1/2 that I had to add, because I also put the 2 in there, I can actually evaluate this expression this way by going left to right in the formula.